very happy to have Sudip again at IISc. He's now in Technion, and he will talk about crossing-symmetric dispersion relation for 1D CFT.
Okay, thanks Arnav. It's nice to be back at IISc visiting again. So I hope people can hear me. Good. So I'm going to be talking about actually crossing-symmetric dispersion relations for in the case of 1D conformal field theories. And this is work done in collaboration with Dean Karmi and Ghsoh Sharma, who are both at Technion. It seems like this is essentially like the group meeting, so I can actually skip most of the introduction that I had planned. Okay, but let's start with some generalities, and then we'll try and go on to the technical details. So just one generality is that as most of you are familiar, is that so what is the idea behind actually dispersion relations? So dispersion. So the main idea is that if you have some function of some complex variable, then the idea is that you want to reconstruct that function from a knowledge of its discontinuities. So that's the essential idea behind writing down a dispersion relation. And one of the most prominent applications of this idea in the context of quantum field theory is for scattering amplitudes, where you write down where you, let's say, you consider, let's say, some 2 to 2 scattering amplitude. Let's say denote that by A. This is going to be a function of, let's say, 2 Mandelstam invariants. Let's call them S and T. And the idea is that we want to reconstruct this object from a knowledge of its imaginary part, or its equivalently what is referred to as the discontinuity. Okay. And typically what you do is that, so this object has some analyticity structure in the complex Mandelstam plane. The idea is that you fix one of the variables and think of it as a complex, as a function of as a function of the other variable, and think of it in the complex plane. And this guy has some analyticity structure in the sense that this has some cuts in the complex plane. So for example, if you consider the complex S plane for a fixed T, then this object has some analyticity structure. There is some branch cut which starts from the 2 particle threshold, and there is some branch cut on this side which should be there by crossing symmetry. And then the idea is that you want to determine this function by writing down some contour which wraps around these branch cuts. And so what you essentially do is that you write down some contour integral like this. So this is just Cauchy's theorem. You choose some point S prime in the complex plane and do some contour like this. So this contour is centered around some point S prime here. And then if this function dies off sufficiently fast at infinity, then you can actually deform this contour and wrap the contour around these branch cuts. So then we can draw a different contour. Which wraps around these branch cuts. Okay, and that leads to a representation which looks like this. Okay, and this is what is often referred to as, let's say, in this case, basically the fixed T dispersion relations, because we are fixing one of the variables. So as I said that the input in this. So the idea here is that if you know the imaginary part of the amplitude, then you can do this contour integral, and then you can get back the full amplitude. And the reason we like this is that this imaginary part actually has nice properties For example, it has nice actually positivity properties. For example, when you take the forward limit, then it is actually a positive quantity. And it is often actually much easier to compute the imaginary part rather than computing the full amplitude. Okay. So that's the idea. Now, what the question that we are interested in is that is there an analogous story for conformal field theories, where instead of considering the 2 to 2 scattering amplitude, we want to consider the 4-point function of some bunch of primary operators in a conformal field theory. Okay. So this most of you know that you can. So for simplicity, let me consider the case where these operators are actually identical external. These are all identical operators. They have the same scaling dimension. Then you know that you can pull out some factors like this, and let's say these guys have scaling dimensions delta phi. So up to this normalization, you can write down a function which is actually conformally invariant in terms of what are called actually cross ratios. So the z and z bar are actually cross ratios, and they are related to the insertion points x1, x2, x3 in some simple way. For example, yes, question. Yes. Yeah. So here, the 2 to 2 amplitude. Yeah. So here, this is the assumption that So there is So in this example that I gave you, there are no other singularities, but you could have some. There could be cases where you have some other singularities. For example, there could be some poles here and so on. But yeah, exactly. So so basically, this imaginary part is basically this discontinuity when you wrap around this branch cut. Right. So the z and z bar are defined in this way. Okay. So what we want is that what we want to do is that we want to write down a dispersion relation for basically for this object g z z bar, where the input will be some kind of an imaginary part, and what we want is that as I said, that in the amplitude context, the imaginary part has nice basically has nice properties. It has nice positivity properties and so on. So what we want to do is that we want to write down a dispersion relation where the input is some kind of an imaginary part which also enjoys nice positivity properties. And that has been, and what that object should be has been understood in recent years. And the role of the imaginary part is played by what is called the double discontinuity of this object. So if you have never heard about this object double discontinuity, don't be worried. I'm going to define it actually soon. So now, for now, just take it that I'm going to define some object, which I'm going to call. So this is a shorthand for what is referred to as double discontinuity. Okay, I'm going to define it shortly, so don't worry. And the idea is that this is going to play the role of the imaginary part in the scattering amplitude context, and this is going to have actually nice positivity properties. So okay, so then the question is that what is the dispersion relation where this object is the input, and so this question was actually answered a few years ago by Dean Carmi and by Simon Caranvo. Sorry. Yes. Yes. Yeah. So I'm going to define it shortly. Yeah. I'm going to define it. Or maybe I should define it now. Okay. Yeah. Okay. Thanks for the question. I should define it first. Okay. So let's define this D disk. So this D disk, so this double discontinuity is basically an object which actually is actually computing actually two ways of analytically continuing this function across its certain actually branch cuts. So what you can show is that this function g of z bar has a bunch of has actually certain branch cuts. For example, it has a branch cut when from z bar when let's say z bar is from 1 to infinity and from let's say from 0 to minus infinity. Okay. So this analyticity structure can be actually seen by expanding g of z bar in terms of conformal blocks, and you can show that it has this analyticity structure. And the way I am going to define D disk is as follows. So this is going to be, so the definition that I am going to write down is holds for external operators being identical. There is a more general formula which applies for when the external operators all have different scaling dimensions, but I am not going to write that down. So this object looks like G. Okay, I am going to write a funny symbol and then I am going to explain what this means. Okay. So this notation means where I have this I basically have this circle going in this direction. What it means is that it means that what I want to do is that in this so what this object means is that in this formula I keep z fixed and I take z bar around this branch cut. Okay. And this arrow basically denotes one way of, or basically one direction of going around the branch cut, and this other arrow denotes the other way of going around the branch cut. Okay. So this is the definition, and what you can show is that unitarity implies. So if we are considering a unitary conformal field theory, then unitarity implies that the disk of GZZ bar is actually positive semi-definite when Z and Z bar are between 0 and 1. Okay, so this follows from unitarity. So right, so that is the disk. So in this case, like So does that answer your question or not?
So
yeah.
Yeah.
So there are branch cuts both in the Z and the Z bar, both and the Z and Z bar variables. So here I am showing the branch cut structured in the Z bar plane, and there is analogous since it is symmetric under Z and Z bar. So the analyticity structure is same in the Z variable. But yeah, right. So here we are not going to do that in the sense that the formula for the dispersion relation that I am going to write down That will involve basically a double integral over, in this case actually, both of these variables. So in that sense, it will be slightly different from this, where we are integrating over just one variable. Okay, right? Yes. Yeah. Yeah. So the discontinuity will be the standard thing, that where you just take the imaginary part across any of these branch cuts. Right. So this is, so I should just mention that this is, that this analytic continuation is being taken with z fixed and z bar equal to, and around z bar equal to 1. Okay. And so this is just a technical comment, is that this is what is often referred to as the T-channel, this is what is referred to as the T-channel double discontinuity. There is, now since you may be wondering that what happens to this other branch cut, so there is an analogous actually definition where you hold z fixed and take the analytic continuation around by moving z bar around this branch cut. There is an analogous definition there, and that object is referred to as the U-channel double discontinuity. Okay. And the main result of Dean Carmi and Simon Caron-Ho in a paper from 2019 was that you can use these two objects as inputs in order to determine the CFT correlator in the following sense, that what they did is that they wrote down a formula which looks like this. I am going to be a bit schematic here, but just to highlight the essential features. So there is a double integral from 1 to infinity plus there is an analogous term for the U channel. Okay. So this is the formula which they wrote down. Where the input is the double discontinuity in two channels around in the T channel, in the so-called T channel and the so-called U channel. And these objects are certain kernels, this KT and KU. These are some kernels which one can explicitly determine. Now it turns out that these kernels are not some simple looking objects like in the amplitude case. In the amplitude case, the kernel is just actually is actually almost trivial. You can just actually guess this. But these kernels are actually, but these kernels, there is no way to guess the expression for these kernels. We actually have to do a long calculation and find it out. And these people actually did it. And this has some complicated form in terms of hypergeometric functions, some complicated dependence on these cross ratios and so on. So I'm not going to write down that form. Yes, yes, exactly. So that was going to be my next remark. Is that basically that this object is not going to be actually a manifestly crossing symmetric object.
And like what you have this limited domain.
Right.
In the fixed T dispersion relation.
Yes. Yes. Yes.
Is there a limited domain of analyticity in the ZZ bar for this?
Yes. Yeah.
I would have expected.
Yeah. Yeah. So that so some of these questions are actually sort of open. Actually, I don't think anybody has actually rigorously studied this. What is the domain of analyticity of these formulas? But these formulas seem to hold within the region of convergence of the OPE. So wherever the OP is convergent, these formulas seem to hold. But if that domain can be enlarged or not, we don't know. Okay, good.
How
Yes.
difficult is it to suppose
Yes.
I wanted to do
Yes.
this for the 2D easing model?
Yes, yes,
2D easing model
yes,
is like
yes.
some simple function.
Yeah, so
That you
2D,
need to do it
yes.
explicitly, right? Check.
Yeah. So for the 2D Ising model, you can do. In fact, in this, I don't know if these guys did it for the 2D. In fact, you can do it because, So these functions are actually, in a sense, universal because these functions don't depend on the scaling dimensions of the external operators. Okay. So once you you can determine these functions once and for all. And then what depends on the theory is going to be this object. So you put that in and so the 2D Ising model can be studied using this. Yes. So so 2 remarks. One we already said, this is not manifestly crossing symmetric in all channels. And second is that right. Yeah, second is that this formula holds only for d greater than equal to 2 CFTs. Okay.
Wait, can't I think of d equal to 1 as some
Yes.
diagonal limit on that way?
You can so that you can take, but the point is that so you can take, but as I'm going to say in a second is that in the diagonal limit we have only one cross ratio, but on this side this formula will still be integrated over actually two cross ratios. So this will not look like an object which you would naturally write down in one dimension, where there is only one cross ratio. Good. So are there any questions about this? Yeah. So the kernels are known objects. In this paper, these kernels were computed. Yes. Yes. Yeah. Yes. Yes. Yeah. Right. Yeah, I can say that again. So these arrows denote basically two different ways of analytic continuation. So here, basically the prescription is that I hold Z fixed and I want to work out the monodromy around Z bar equal to 1. And I go around in one direction around the branch cut, which is this guy. And here I do the same thing, keep Z fixed, take monodromy around Z bar equal to 1, but in the opposite direction.
So it's like 1 minus Z bar going to 1 minus Z bar times e to the power
Yeah.
2 pi I in one case?
Yes,
minus
exactly.
pi I.
Exactly. That's right. Exactly. That's right. Yeah. So, okay. So let's see. Yes.
I've often wondered when I've seen
Yeah.
these papers,
Yes.
and so far as the S matrix story was concerned, there is
Yes.
a reason for looking at all this.
Yes.
To put bounds on Wilson coefficients and
Yes.
things like that.
Yes. Yes.
But
Yes.
why were Dean and Simon
Yes.
looking at this problem
Yes.
anyway? What is the big goal
Yes.
that they had?
I guess one motivation was to actually sort of get so one motivation is of course to get a formula which is sort of similar in spirit to the dispersion relation for this matrix, where the imaginary part, whatever plays the role of imaginary part, has to have nice positivity properties. And then there is this Lorentzian inversion formula, which I am going to talk about in a second. So basically, so maybe I should actually say the Lorentzian inversion formula and then say it. So I'm going to mention that. Yeah, so these are the good points that people are bringing up, but let's see. So what is so how does one actually derive a formula like this? So I'm not going to actually tell you all the details, but one essential ingredient that goes into the derivation of this object is what is known as the Lorentzian inversion formula, which was found by Simon. And the Lorentzian inversion formula is basically a formula which extracts the OPE data of this correlation function from a knowledge of its discontinuities. So that has some structure like this. So what you do is that, okay, so the formula looks something like this. Okay, where this C delta j is an object which is called the OPE function, and this object actually has poles at the location of the physical operators in the spectrum of your theory. Okay, and the residues at these poles basically are equal to actually the OPE coefficient squared, which appeared in the conformal block decomposition of this object. Okay. So this is actually, there is actually a minus sign, but this is actually the residues at these poles is minus of the squared OPE coefficients. So in the and now there is a formula for this object. Let me write down a formula for this guy. So there is some normalization which is not going to be important, but there is some measure. There is some kernel. Delta plus D-1. Okay. So so let me just say what these things are. So this guy is some normalization which depends on delta and the spin. Not really important what the details are. This is some measure, and this is actually just a conformal block, although it is sort of a funny conformal block where the spin and the dimension labels are sort of inverted, and this is often referred to as an inverted block. And then there is the double discontinuity. And the idea is that this is a representation for this object, and what you can do is that by doing this integral, you can actually try to figure out where the poles of this object are in the delta plane, and this object is going to have poles in the delta plane at the location of the physical operators in the spectrum with residues which encode the OPE coefficients. Okay. Mu is some measure. Mu is some measure which depends on W and W bar. I am not going to write that down. Right. And then there is a similar formula for Cu which is obtained by interchanging some labels. Okay. So this is what is known as Simon-Caron-Ghosh Lorentzian inversion formula. Okay. The idea is that this is an object which extracts the OPE data of the theory from a knowledge of its double discontinuities. Now coming back to Aninda's question, so what this dispersion relation does is that it actually in a sense resums this object. It in a sense resums this object over the full spectrum. because this is actually delta by delta. But what this object does is that it actually repackages everything and into one big formula. Yeah. Yes. Yeah. No, so so there are other kinds of dispersion relations, which some of which actually, which don't involve the double discontinuity, which involve the single discontinuity. But here, what we are saying is that I want to demand, or let's say my wish is that I want a formula where the input is the double discontinuity rather than the single discontinuity. And much of the complication which appears regarding the computation of these kernels appears because of this requirement that I want the double discontinuity instead of single discontinuity. Yes.
One reason why I can think of a representation of this kind is if I want to bootstrap.
Yeah, exactly. So that yes.
Do that, I require to feed in a conformal block on the right hand side.
Exactly.
The
Exactly.
The question is that I know that these K's look
horrible. Yes, they do. Yes.
So there is no hope between
Yes.
CFTs and analytic.
So there is not in the most general case not, but in some simple cases you can do it.
Yeah. So basically, if I wanted to actually come up with some
Yes.
good set of blocks, those
Yes.
will be numerical.
Yes.
There are
Yes.
no analytical.
So analytically, analytically you can do it in the sense that Yes. Right.
Formula.
Right.
In the 1D formula, if I wanted to have a crossing-symmetric block for a fixed
Yes.
operator,
Yes.
then can I do that
Yes.
block analytic? Do I know that block analytic?
So as I am going to say is that you know that block analytically when the dimension of the external operators they assume special values. So in that case one can write down somewhat simpler looking formulas, or not really simple, but you can write down closed form formulas. So as Anand pointed out, that one of the motivations for writing down a dispersion relation like this is to actually do bootstrap with this. We want to put constraints on the CFT data and so on. And these kinds of dispersion relations can also be used to put constraints on the values of the correlation function itself. So yes. Exactly. So in practice, people don't quite actually do it. What people do is that people do an expansion on both sides around, let's say, z equal to 0. They match powers on both sides, and they basically get some constraints. And in some cases you can evaluate them, other cases you do it numerically. Okay, great. That was a long introduction. Okay, so now let me go over to the 1D case. Right. So now I am going to focus on 1D CFTs. Okay. So what are what are 1D CFTs? So in one dimension, so there are various ways of actually thinking of 1D conformal field theories. One way in which you can think of them is that you take any higher dimensional conformal field theory, and if you consider, let's say, some correlation function, let's say like the 4-point correlation function, what you can do is that you can restrict this correlation function to what is called the line, where in this case you choose, let's say, z equal to z bar. Then what happens is that with this restriction, any 4-point function in d greater than 1 CFT at z equal to z bar is going to become a function of only one cross ratio. Okay, And in that sense, you can think of it as just a one-dimensional conformal field theory, where basically the conformal group is just SL2R. In this case, which is of course a subgroup of the full conformal group. Okay. So this is one way of thinking about 1D CFTs as sort of as restrictions of higher D CFTs on the line. But there are also many interesting systems which exhibit actually one-dimensional conformal invariants, which are interesting to study. For example, there is this long-range 1D Ising model. Okay, so let me write down some examples. So there is a 1D long-range Ising. This is just to motivate that the 1D case is not just of academic interest. 1D long-range Ising. Then one can consider line defects in D greater than 1 CFTs. And another example is that one-dimensional conformal field theories can be thought of as the duals of they can be thought of as holographic duals of actually quantum field theories in two-dimensional anti-de Sitter spacetimes. So if you want to study quantum field theories in ADS2, then you can define basically, if you consider correlation functions of quantum field theories in ADS2, then take the limit where the insertion points go to the boundary, then that defines a conformal invariant object because the isometries of ADS2 is essentially SL2R. Okay, so that ADS2 is also near horizon geometry of extremal black hole. Yes, yeah. So then it has interesting applications for studying black holes as well.
Have people done that using the, say the 1D bootstrap?
No, I don't think people have done that. Yeah. So that also you can do. But none of those actually. Exactly. But one thing I should point out is that basically most of this one-dimensional conformal invariant systems are actually not local, in the sense that, so this is technical comment that in one dimension you can show that the stress tensor actually vanishes. So the theory is actually topology. If you insist that if you want to make a local theory in one dimension which is conformal invariant, you can't do it. So then most of these theories are actually non-local in some sense.
By the way, this 1D long-range Ising model, does that exhibit phase transitions?
So this admits a phase transition because of the fact that the interactions are not local, because otherwise in one dimension there is no phase transition. So the stress tensor in all of these cases, So if you consider a system that is intrinsically one-dimensional, that actually does not have a stress tensor. But you can think of it as coming from some higher D CFT. In higher dimensions, of course, you have a stress tensor. Okay, great. Let's see, what else do I want to say? Okay, now let's come to the meat of the talk. Okay, so what we want to do is that we want to actually replicate, we want to actually sort of find an analogous formula in one dimension, and that I have tried to motivate to you that it is of interest to do that. And okay, before doing that, one more reason why you would want to do it is that actually the crossing equation is somewhat simpler in 1D. Okay. So the crossing equation in one dimension looks something like this. So if you expand in conformal blocks, then okay. So this has to be equal to 0, where these G's are what are called actually SL2R blocks. Okay. So this is a statement of crossing symmetry which just says that that the expansion of the correlator in S-channel conformal blocks should be identical to the expansion of the correlator in terms of T-channel conformal blocks. And this equation in one dimension, as you see, depends only on just so this just depends on just a single cross ratio, as in contrast to its counterpart in higher dimensions, where this will involve two cross ratios. So this equation is much simpler, and in recent years there has been a lot of progress in trying to extract actually consequences on the OPE data from this equation in one dimension. Okay.
I don't want to derail your talk, but
yeah, sure.
can I just ask,
Yes.
is my way of
Yeah,
thinking
right,
correct?
right.
Because of the fact that you mentioned
Yes.
the stress tensor vanishes in
Yes,
1D,
yes.
If I wanted to think in the language of these word identities, define conformal invariants, the only way that I can do it is to think of it as a limit of some high dimensional number.
Yeah, so the
I can't really define a CFT in one dimension because of stress
yeah,
tensor.
so that is true. So another way of saying it is that in this case, so basically all the symmetry charges are there, but the symmetry charges are not expressible in terms of local currents. Great. So right. So the point is that this crossing equation is simpler, and there has been a lot of effort in trying to sort of actually analyze this in detail in recent years, and people have learned a lot of things out of it. Okay. So right. Okay. So in one dimension, once again, our object of interest is going to be this 4-point function of identical operators that up to this normalization is going to be a function of a single cross ratio. Okay. And we want to write down a dispersion relation for this object. So so one thing I should mention is that in one dimension there is no spin. Okay. But you can have statistics in the sense that you can ask is that if I interchange, if I swap these two guys, then in that case do I get a sign factor or not? So depending on that, so if you don't get a sign factor, then then the operators will be referred to as actually bosons, and if you get a minus sign, if you swap two operators, then these will be referred to as fermions. Okay. And it turns out that there is a different dispersion relation which applies in the bosonic case, and a different dispersion relation which applies in the fermionic case. Okay. Okay. So let me write down the main result, and then I will briefly sketch the derivation. So the result is the following: is that for 1D CFTs, the following representation exists. okay, where where the double discontinuity is in the 1D case is defined as follows, which is just a restriction of the higher D formula.
Sorry, you want W?
Yes. Sorry. Yeah. Good. Thanks. Right. So, okay. Sorry for changing notation slightly, but this is what people do. Okay. Where this G plus is basically is a similar object which I defined before with G with this called the arrows, where once again the definition is kind of the same. Is here that this object actually has branch cuts which extend from z equal to 1 to infinity, and this G plus basically means that you want to actually consider the analytic continuation around the branch cut which extends from 1 to infinity, and this z plus I epsilon means you do the analytic continuation one way, z minus I epsilon means you do the analytic continuation the other way. Okay.
So the range of integrals,
Yes.
the higher dimensional
Yes.
formula was also
So the range of integration in the higher D formula was also 0 to 1 in where in the case where you have the T channel D disk, in the U channel it's minus infinity to 0. Right. Good. So that is D disk. The other ingredient in this formula is this kernel. And now there is one crucial difference as compared to the higher dimensional case, is that this K depends non-trivially on the scaling dimension of the external operators, which was not the case in the higher dimensional case. In the higher dimensional case, if you compute the analogous kernels, they are universal. Okay. Right. So what and the other thing is that this object is actually manifestly crossing symmetric, and that happens because this kernel turns out to have a certain symmetry. So this comes out as a result of the computation that this kernel has this kernel has this symmetry property, and so therefore 1D dispersion is manifestly crossing symmetric.
something has
Yes.
to give.
Yes.
Because the other
Yes.
case,
Yeah.
the way that we think about
Right.
the story, that
Right.
when we
Right.
think about
Right. Right.
manifestly crossing symmetric dispersion,
Yes.
we
Yes.
have these locality constraints.
Exactly.
So you have something similar
Yeah. So here we will have something similar in the sense that this object will actually give us the expansion of the 1D correlator in terms of Polyakov blocks. So
those
yeah.
sorry,
Yes.
in your nomenclature, the Polyakov
Yeah.
blocks are
So.
bounded or not?
So in my nomenclature, the Polyakov blocks are okay. So I'm going to assume that So another technical remark is that this dispersion relation that I'm going to write down, I'm going to assume that this is for AJ bounded correlators, and then this Polyakov blocks will be actually crossing symmetric sums of actually Witten exchange diagrams.
But Witten is
Yeah,
sometimes
yeah.
in our language, what
Yes.
AJ bounded?
Right.
So is that the same in your case?
I think in our case these Witten diagrams are AJ bounded actually.
But then where the constraints coming from?
Yeah, I mean the constraints come from So the constraints come because this gives us an expansion in terms of Polyakov blocks, but we want to demand that this is identical.
There are these spurious poles.
Exactly. Yeah. So we demand that this is identical to the conformal block expansion, and yeah. Right. Yeah. Okay. So yeah. So for everyone else, let me just say that once more. Is that yeah. So what is going to happen is that here, if you plug in basically the conformal block expansion, then yeah. Okay. So yeah. So what you can do is that you can plug in the conformal block expansion. Suppose you let's say you plug in the T-channel conformal block expansion, which looks like this. Okay, let me not write all the details. Okay, and so if you plug this conformal block expansion here, then you get a representation for the correlator, which looks like and then and d disk of T-channel conformal block. Okay, so what I'm going to do is that we can define this object, we can define this guy, which is the integral transform, which is the integral of the double discontinuity of the T-channel conformal block times this kernel. We can call this some object, let's say P. And then what this gives us is that this representation gives us an expansion of the correlator in terms of these objects. And what you can show is that this object is nothing but crossing symmetric sum of Witten exchange diagrams in a DS2. So yeah. So and then, as Anindya was pointing out, is that basically the constraints on the spectrum, they come from basically demanding that this expansion is equivalent to expanding in standard conformal blocks, let's say the S-channel conformal blocks. Okay, and yeah, and then demanding this leads to actually constraints on the OPE data. Okay, so right. So let's highlight this because this is the main result.
Sorry, how are you
Yes. Yes, I'm going to write down a K for you. Yes. Okay. Okay. By the way, how much time do I have on up? Is my time up? Huh?
How long we need?
Maybe 10 minutes. Good. Okay. So yeah. So what is the okay? So how does one derive a formula like this? So let me sketch the idea. So the idea is that the idea is follows. So what we can do is that we can actually we start with the expansion of Gz in terms of what are known as actually partial waves. Right. Sorry, not D, half. There is some normalization, and then there is the partial wave. Okay. So the Xi's are what are referred to as partial waves. These are actually eigenfunctions of basically the Casimir differential operator, and these form a complete orthonormal basis, and so therefore you can expand any function in this basis. Okay. So now, so then what one does is that, and the crucial object here is this guy. So this guy actually has poles at location of the physical operators in the spectrum, and the residue here encodes the OPE coefficients. So you can recover the standard conformal block expansion by doing a contour deformation of this object by deforming the contour towards the right, encompass basically making a contribution from these poles and so on. Conformal partial wave is crossing symmetric. No. So this representation does not is not crossing symmetric. Okay. So then, So
From here you can obtain this one. You assume certain
yes.
high energy follow behavior.
So you assume follow behavior in the sense that it is assumed that that these guys are actually so this arc is actually in the delta plane. It's not in the z plane. So you assume that in the delta. So that actually is true because you can show that these OPE coefficients decay and so on. So you can actually, so it's okay to close the contour. Right. So now what? Okay. So let's see. Okay.
Are these polynomials smooth-sided, like in analogy with this matrix?
So psi delta is not a polynomial. So this I should have said that the psi delta is basically some linear combination of conformal blocks. Yes, it's So it's this guy. So it's some normalization times g delta plus some other normalization times g of, in one dimension shadow is taking delta to 1 minus delta. Okay, right. So so next what we want to do is that we, since we want a formula in terms of double discontinuity, we need to get that from somewhere. So what we do is the following. So what we do is that there is a representation of this object, this I delta, which I'm going to refer to as the OPE coefficient function. There is a representation of this in terms of the D disk, which looks something like this. G of where here once again this is some kernel which explicitly depends on the scaling dimension of the external operators of external operator delta phi, and this integral representation was found by Dalimil Mazak in I think in 2018. Okay. So I am not going to go into the details of what this kernel looks like. This kernel also turns out to be horrible. But what you can do is that if one can find explicit basically closed form expressions for this kernel when the delta phis take special values. So when delta phi is, let's say, either let's say positive integers, or when delta phi is actually half integers. In those cases, it turns out that the expression of these kernels actually simplify quite a lot, and one can find actually closed form expressions for this. And the dispersion relation that we have been able to derive or basically the kernel that we have been able to derive is only in these cases. So we don't know as of yet what is the kernel for more general values of delta phi.
If you, yes. So there is this famous theorem called Carlson's theorem. That
yes,
the
yes, yes,
value of the
yes.
function at each point
Right, right,
has an
right.
exponential fall off, then you know
Right,
the
right,
function. You
right,
quantify that?
right. Yeah, so yeah, I mean, maybe one can do that. I mean, we have not tried, but yeah, I mean, there is another way of actually sort of determining these kernels is that these kernels satisfy and these kernels satisfy actually some integral equations, which actually follows from this symmetry property and the fact that that the double discontinuity of the kernel is actually a delta function. If you take double discontinuity with respect to z, this is actually a delta function. This follows basically because of consistency of this formula. And so these two conditions and some fall off condition on k gives you some integral equations. Those integral equations, actually it is fairly easy to numerically solve those integral equations, and one can determine these kernels. Yeah, but just to complete the chain of logic, so here what we do is the following. So we take this integral representation for the OPE coefficient function in terms of d disk, this guy, and we plug it back here. Okay, we take this formula. There is a formula for I delta. We plug it back here. Then what you can do is that you can swap the order of integrals, swap the order of the W integral and the delta integral, and then yeah. So you do that. So then you will get some formula which looks like this. There will be some integral here of which will involve the kernel. I am not writing all the normalization factors and so on. Times whatever, times your d disk. Okay, and so this has some contoured integral that you need to compute, and so this contoured integral, of course, you can compute only if you know this object, and we know closed form expressions of this object in these cases, and so you can, although and so you can actually plug those guys here, do this contour integral, and you can derive expressions for this kernel. So this kernel that I mentioned is basically done, it's basically obtained by doing integrals of this form. And then it's a complicated mess to do these integrals. If you so actually Mathematica cannot help you in doing these integrals. So what you have to do is that you have to find old Russian books on this table of integrals and so on, and you have to So what you can do is that you can write it as when you do the contour deformation, you write this object as a sum over some poles. So you have you have some representation in terms of an infinite sum. Now you have to do that infinite sum, and actually Mathematica can't do such infinite sums. So then you go and dig up old Russian books, and then you find that actually those infinite sums actually have explicit answers. They actually have explicit closed form answers in terms of z, w, and delta phi. Okay, so I'm going to end in 2 minutes, but since I was asked to write down a formula for the kernel, I'm going to write that now, and that will probably be the longest formula that I'm going to write in the talk. Yes. Yes. H delta. No, H delta is actually not hypergeometric. H delta is so H delta is involves some hypergeometrics, but then there is also some logs and so on. So so it's a slightly complicated mess. But okay, so formula for kernel. So that's the last thing I will write.
Higher dimensional formula,
yes.
You have adopted a similar strategy. Is that?
So this I should have mentioned that the strategy that we adopted here is not really a new strategy, because this is exactly how the dispersion relation in higher dimension was actually found. That in higher dimension there is also a formula like this, which expresses the correlator in terms of conformal partial waves, and then you plug in actually Simon-Caron-Ghosh Lorentzian inversion formula in this, swap integrals, and then do the same thing. But the only so the difference with that case is that in case of Simon's Lorentzian inversion formula, this kernel is some universal object. So you know this once and for all. But here we have to compute it case by case. Okay, so I'm going to write down one formula and then I'm going to stop. So I'm going to write down the formula in the case of the fermionic dispersion relation. There is a similar looking formula for in the bosonic case. So what I mean by the fermionic case is that I'm going to write a formula for when the external scaling dimensions are half integers. And in this case, one can show that this kernel looks like this. Right. Right. So okay. This formula is long, but it is nice, so I'm going to write it. This F stands for fermion. It's a label to distinguish with the bosonic case. Please bear with me for 1 minute. Yeah, so this is this log factor that I was talking about, which comes here, and then there is some function which you can evaluate by acting repeatedly with some differential operator. Interestingly, this combination that appears here is related to actually contact diagrams in EDS2. This is the d bar function, and okay, requires one full. I'm going to say 1 second, and plus set by. Yeah, so curl dd is a differential operator which looks like del, in this case del z dz. So this is this differential operator. So as you can see, this formula is not nice, but it has some nice structure. That it has a thing that it has these logs and the structure. So I'm not specifying some more details about this. So these objects are actually certain polynomials in this variable w. So it's a polynomial of degree 2 delta phi minus 2 as well. And these can be figured out on a case by case basis. We don't know in general exactly what is the general form of these polynomials, but if you specify to me some half integer value, then I can tell you what these polynomials are. So this is the formula that one can write down in the case of actually the fermionic dispersion relation, meaning delta phi belonging to these values. There is one formula there is a very similar looking formula for in the bosonic case, where the scaling dimensions take on integer, values. So that's what I wanted to say. And okay. So maybe I should end, but let me summarize. So the main, if you got lost in all the technical details, then the takeaway message is basically that in one-dimensional conformal field theories, one can write down a crossing symmetric dispersion relation in terms of the double discontinuity, which looks like this. It has a kernel that explicitly depends on the scaling dimension of the external operators. And in fact, this dispersion relation can also be applied to higher dimensional conformal field theories. If you think of the higher dimensional conformal field theory correlator as being restricted in the region of cross ratio space where z is equal to z bar. Okay, and one can determine closed form expressions for these kernels by sort of combining the expansion of the correlator in terms of partial waves and the Lorentzian inversion formula, which is applicable for 1D conformal field theories. You can combine those two things and determine closed form expressions for this K, although these closed form expressions can be found explicitly in only certain cases. So a goal for the future.
Something very basic.
Yes, of course.
If you did this step
Yes.
in higher dimensions, you don't
Yes.
get something
Yes.
crossing symmetric.
Yes.
But
Yes.
how do you get something crossing symmetric here?
So here we get crossing symmetric because of essentially of this guy. So this Lorentzian inversion formula in 1D is actually a crossing symmetric object, in the sense that if I plug in the T-channel conformal block decomposition here, then this is going to yield the coefficient function for a crossing symmetric object. So so since but in this form, it's not very clear actually what it means by this being crossing symmetric. But once you get the dispersion relation, it's kind of obvious from its form why it is crossing.
And also, I guess the challenge in high dimensions is that the crossing symmetry is not simply the UV interchange. There is also the
So there is a use exactly that. Exactly. So since in the 1D case, this I did not mention in detail, but in the 1D case we have access to basically this S and T channel OPEs, but the U channel OPE we don't really have access to. And this formula makes manifest the symmetry in the ST channel. So it's crossing symmetry in that sense. So one technical goal for the future is to be able to derive these kernels more generally, either analytically or let's say numerically, and then apply this for actually constraining CFT data. Do actually bootstrap with this.
One fun thing that you can say immediately is that there is this work that Nima did, where they
yes, yes.
create a connection between 1D and
Right.
cyclic polydromes.
Right.
So of course, then it will expand in terms of
Right.
the
Right.
in crossing-symmetric blocks.
Right.
What they did
Right.
was
Right.
expanded in terms of SL2R blocks and then
Right.
they took a slice of that,
Right.
which
Right.
intersected with the crossing-symmetric
Yeah.
condition. Now you actually can do this.
Yeah.
Then
Yeah.
see whether
Yeah.
the cyclic polydrome. So what exactly
Yeah.
happens to the polydrome structure?
Yeah, exactly. Yeah, so I was actually trying to think something along those lines. I don't have anything concrete to say, but there is some interesting positivity properties of these kernels actually. So one last comment is that these kernels are actually, you can show that a priori it's not obvious, but you can show that these kernels are actually positive in the region whenever z is between 0 and 1, or equivalently within this integration region, that actually positive. So why it is positive? So yeah, so an interesting mathematical question is to understand why these things are positive. Is there a representation of these objects that makes this positivity manifest, and so on. But yeah, okay. So I think I have short over my time. So thanks.
Is there any experiment unitarity?
Unitarity has not really been used here as such. So the only place unitarity plays a role is that these guys are actually positive. This is squared, so it's some real number. But the C5, sorry.
But that's a notation that you need not be positive.
That is not used in universal.
Yeah, exactly. So explicitly unitarity is not used anywhere.
Also, if you think of it as a limit of a high dimensional thing,
Right.
your C squares are basically a combination of the high dimensional.
Exactly.
That need not have any.
That need not have positive. Yeah, I agree. Yeah, true. Yeah. Okay.
So this order is log structures.
Yes.
The cancel that we have the singularity in this log singularity.
Good. Yeah, so that is actually a very good observation. So yeah, so it turns out that when you plug these kernels here, so these logs are kind of important, but but these logs are somewhat funny. And in fact, if you try to expand this side in terms of S-channel conformal blocks, then there are no logs, of course, because the S-channel conformal block is regular around z equal to 0. So basically these log contributions actually have to drop out. And the sum rules or the constraints on the OPE data, they come from demanding that such log terms vanish. These are exactly. So these give exactly the Polyakov conditions. Yeah. Right.
This is very interesting because I've often wondered whether the Polyakov conditions give you X. And so the way that people have formulated it, there are these null constraints or locality constraints which
Yes.
are crossing-symmetric
Yes.
or whatever.
Yes.
And then there are these Polyakov conditions.
Right.
And nobody has actually ever addressed whether these are these carry the same information or is one of the subset of the other, which one is the subset of which. So nobody has actually classified. But here you are saying that the only condition that actually you get are the Polyakov conditions.
Exactly.
You don't have
Yes.
analog of the
Yeah.
null
Yeah.
constraints.
Yeah. Analog of null constraints. We don't have. Right.
What is meant by non-local? So you said the CFTs are non-local.
This is the constraint.
No, so in this
Oh, here. Yeah.
some power subsets are not allowed or something like that.
Yeah. In this case, like you may be familiar with the S-matrix story, where when you write down a dispersion relation for the S-matrix and then you expand the dispersive representation in the low energy expansion, then you get some spurious powers. And those spurious powers cannot appear in the local theory; they have to cancel out. So these give constraints. I don't know exactly in that language if, I don't think exactly in that language there are those kinds of things, but there are spurious powers in the following sense, that what you get is that from these kinds of logs, and there are log z's in all bunch of places, but from there you get spurious powers which look like, so you get two kinds of spurious powers. You get spurious powers which are like z to the n, and spurious powers which are like z to the log z. z to the n log z, something like this. And then these have to cancel out, and the cancellation of these two sets of spurious factors leads to two sets of constraints on the OPE data. And these two sets of constraints are precisely the two sets of sum rules that one gets in the 1D Polyakov bootstrap. Yeah, no. So these constraints, okay. So schematically, these constraints look like this. So this, so if you match powers on both sides, demand that these cancel out, then what you will get is that you will get some constraint like this. So this is what people write in this notation: alpha n delta and beta n delta. So here this alpha n delta and beta n delta are obviously some numbers, but these alpha n's and beta n's have some representation in terms of these kernels. So these are integrals. So this, yeah. Yes. So the integrals are doable in the sense, So what you do is that you can plug in basically the conformal block expansion here. So this is, and then if you know the kernel, then you can do the integral. So with this kernel you can actually, so you can determine what explicitly you can determine what this alpha n's and what this alpha n and beta n's are actually. So this is not just some schematic thing. This you can explicitly work out. No, these are no. I don't think so.
There is a compromise in delta. You basically have.
Exactly. But what kind of functions are these? So these are functions which actually have certain properties. In some cases, you can show that. So these are what are known as actually dispersive functionals. They actually have double zeros at the location of double trace operators, where double trace. Exactly. So where double trace means these kind of operators, or 2 delta phi plus 2n plus 1. So this has double zeros, and this has actually positivity properties and so on. So so these you can use to put bounds on OPE coefficients, bounds on the gap above the identity operator, and these sort of things people have done.
Dalinen was using similar techniques to actually have another story about this closed function problem. He was using exactly the same functions, right? Or maybe not.
I think they are the same kinds of functionals.